Welcome to the debate. Today we're going to tackle what is arguably the most enduring and disruptive foundational crisis in modern physics, the true nature of the quantum state, psi, and whether it actually corresponds to an objective element of physical reality.
Right. And this debate, it's not new at all. It's really the modern iteration of that huge philosophical standoff that defined the early days of quantum mechanics. Pitting the operational, very pragmatic worldview of Niels Bohr against the relentless quest for completeness and objective reality led by Albert Einstein.
Exactly. So the central question we're facing today, and it really does echo that historical conflict, is pretty stark. Must we accept that the quantum state is fundamentally relational or epistemic, a guide for our beliefs about outcomes? Or does the pursuit of a truly complete theory, one describing objective reality, inevitably introduce some unsettling explicit non-local dynamics? Or maybe even a fundamental modification of quantum theory itself?
I'm going to take that latter position. My argument is that a complete physical theory, it must provide a coherent, observer-independent picture of reality. And that means we need alternatives that actively resolve the conceptual crisis that's just inherent in the standard formulation.
And I'll be advocating for the former position, that quantum mechanics is, at its heart, a tool for managing information and describing relative states, which is perfectly consistent with its undeniable operational success. I'm going to argue that demanding an objective picture leads to, unnecessary complexity and some serious metaphysical excesses. I get it. I see why one desires an objective picture. I really do. But let me give you a different perspective, one that values consistency over, say, pictorial completeness. The non-controversial, tested core of quantum theory is purely, it's operational. It reliably calculates the probabilities of outcomes using the Bohr rule. The initial success of the Copenhagen interpretation, it really rested on accepting indeterminism and using the wave function not as a description of some objective field, but as a probability amplitude, whose significance is only realized when the system interacts with a classical apparatus. And modern interpretations just refine this. Take quantum Bayesianism or cubism. It treats the quantum state entirely as an agent's personal judgment, a degree of belief about future measurement outcomes. So if psi represents my personal knowledge, then when I perform a measurement and the wave function collapses, that collapse is just a change in my local personal state of information.
I see that attempt to redefine the problem, I do. But I'm sorry, I just don't buy that instrumentalist recipe. Relying solely on operational success feels like a philosophical surrender. Physics should aim for understanding reality, not just predicting outcomes. We have to heed the challenge raised by Einstein and his colleagues. Is the theory correct and is the description complete? Operational correctness just does not guarantee ontological completeness. The fundamental challenge, which the standard approach just neatly sidesteps, is a measurement problem. The Schrödinger equation describes the wave function evolving unitarily, smoothly, deterministically, often into a superposition of multiple possibilities. So how does this indeterminate, multifaceted superposition yield the definite, singular outcome that we actually observe in the laboratory? Copenhagen offers a formal description of the transition, sure, but ultimately it feels a bit like an admission of ignorance about the underlying physical process. This is where alternative frameworks that restore objective reality really solve this tension. For example, take Bohmian mechanics or pilot wave theory. It provides a complete objective description by positing two things: the universal wave function, psi, and the precise determinate positions of particles, what Bell called the beables. The particles follow definite trajectories guided by the wave function at all times. So this framework, it restores determinism, it eliminates the measurement problem entirely because particles always have definite positions, and it provides that ontological completeness. This completeness, this full metaphysical picture of reality, is worth pursuing even if it forces us to confront some uncomfortable features, like non-locality.
You champion completeness, but this comes at a massive philosophical and structural cost. You embrace Bohmian mechanics, which, though deterministic, entails explicit, mandatory non-locality. The non-local correlations that have been universally confirmed by Bell tests, they demonstrate that local causality simply must be rejected. That means the definite position of a particle here must be instantaneously influenced by the position of a distant entangled particle, no matter the distance between them. And while this coordination can't be used to transmit usable information faster than light, which ensures locality for macroscopic causal influence, you are choosing a theory that requires hidden instantaneous coordination across vast distances just to restore a determinism that we can never observationally access or verify. I find that, well, deeply inelegant. Why introduce action at a distance into the fundamental fabric of reality if the alternative, treating psi as information, maintains locality and coherence?
That's an interesting point, though I would frame it very differently. Bell's theorem, it forced us to choose between two pillars of classical physics: local causality and objective reality. We choose to retain objective reality, the fact that particles have definite properties at all times, by accepting non-locality. It might be inelegant, as you say, but it is a consistent description. And what's more, if you insist on strict locality and unitary evolution without non-locality, you have to accept the alternative cost, which is the ontological extravagance of the many worlds interpretation. MWI gets rid of wave function collapse entirely by asserting that measurement causes the unitary evolution to branch the entire universe into an infinite number of unobservable, non-interacting worlds, just to realize every possible outcome. That is hardly parsimonious. So the cost of MWI isn't non-locality, it's the complete multiplication of ontology just to save unitarity.
The ontological status of MWI is certainly a complex area, I'll grant you that, but it provides a clean, self-consistent framework. It derives the appearance of collapse from deterministic, unitary dynamics alone, based on relative states. It may be extravagant, but it doesn't require introducing strange, non-local forces dictating particle paths.
But we don't have to choose solely between explicit non-locality, like in Bohm, and ontological extravagance, like in MWI. If you find the cost of many worlds too high, maybe the answer isn't ditching the concept of collapse entirely, but fixing it by embedding it into the dynamics itself. And this brings us to objective collapse theories like continuous spontaneous localization, or CSL. CSL proposes a slight stochastic modification to the unitary Schrödinger equation. So instead of collapse being some arbitrary external event triggered by an observer, CSL introduces a universal objective physical mechanism, a sort of continuous random noise that naturally and spontaneously collapses large superpositions quickly while leaving microscopic systems unperturbed. Crucially, CSL treats psi as ontic, meaning it is a physical reality, and it modifies the dynamics to make it physically collapse. And the critical advantage of CSL is its testability. Unlike interpretations, which just offer different metaphysical readings of the same math, CSL actually predicts physical effects that deviate from standard quantum mechanics. For instance, CSL noise should cause levitated nanoparticles to spontaneously heat up or diffuse slightly more than predicted by environmental factors alone. This transforms the measurement problem from a philosophical debate into a falsifiable experimental program.
I see why you think that, and the prospect of an experimental resolution to this deep problem it's very appealing. But I would argue that CSL is an ad hoc modification that unnecessarily complicates the formalism. Standard quantum mechanics, when you pair it with the concept of environmental decoherence, already provides a compelling physical picture for the appearance of classicality. Decoherence explains how entanglement with the environment, say scattering a single stray photon, rapidly forces a superposition to appear as a classical mixture of states. This process is, for all intents and purposes, irreversible, and it scales naturally. The standard approach requires no arbitrary non-unitary terms. Now, about your claim of falsifiability, the experimental window for testing CSL is extremely narrow, right? It's right where environmental decoherence meets the proposed CSL noise floor.
Standard decoherence rates, driven by universal sources like blackbody radiation or gas collisions, they continuously increase as the mass and size of the object increase. This noise increases indefinitely.
In stark contrast, the CSL model predicts that this noise rate should eventually saturate to a constant maximum value once the object reaches a certain characteristic size. So if these sophisticated experiments with massive macroscopic mechanical resonators show that the decoherence rate continues to climb in proportion to mass, and it doesn't show this predicted saturation plateau, then the standard unitary evolution, where classicality emerges solely through entanglement and decoherence, is reinforced. In that scenario, the burden of proof is right back on those who demand objective collapse dynamics, forcing them to justify modifying a perfectly consistent theory.
That's an excellent summary of the empirical challenge posed by CSL. But let's get back to the epistemic position you hold, specifically cubism. If you're claiming that the wave function is purely personal belief, a tool for me to manage my information, I have to challenge its internal consistency. If the wave function is just subjective judgment, why is the Bohr rule universal? I mean, every agent, regardless of their cultural background, their history, their personal biases, applies the exact same probabilistic rule to the exact same physical system and achieves the same universal success rate. Doesn't that universal success strongly suggest that while the state might be interpreted as personal knowledge, the Bohr rule itself, the mechanism for predicting outcomes, must be rooted in some deep objective structure of reality that goes beyond mere subjective belief? How do you square that circle of subjective state with universal prediction?
Well, that is the essential insight of cubism, though it often gets misunderstood. The universal success of the Bohr rule isn't due to psi being an objective external field. It's due to the structure of quantum measurement itself. The Bohr rule is simply the normative constraint, the logic, if you will, that any rational agent must adhere to when interacting with the quantum world. The structure of reality mandates how probability updates must occur, but it doesn't mandate what the probability assignment is before the interaction happens. The consistency we observe is about the nature of quantum interaction and the constraints on information acquisition, not the existence of an external objective psi. The operational framework handles this cleanly. Psi is an accounting device for correlations and probabilities. It maintains a paradox-free framework, provided we accept that objectivity has to be redefined as relative or relational, just like an RQM.
But this brings us to what I think is the most compelling physical evidence against the purely epistemic view. If psi is merely a state of knowledge, the map, it shouldn't be able to influence reality, the territory, in a manner independent of local forces. Yet, it clearly does. I mean, just consider the Aharonov-Bohm effect. In this experiment, electron trajectories are measurably influenced by a magnetic vector potential that is confined to a region that the electrons do not classically enter. The electrons are never locally exposed to the magnetic field itself. Yet, the quantum phase, governed by psi, shifts demonstrably. This phase shift is a direct, observable consequence of the wave function's influence, exerted non-locally through potential fields. This observation powerfully suggests that psi must correspond to a real physical structure, not just a mental accounting tool. The wave function is acting as a physical field of potentiality, guiding the particle even when local forces are absent. If psi were only knowledge, this physical, observer-independent impact would be deeply, deeply mysterious. The search for a theory where psi is ontic is motivated by exactly this kind of physical impact, steering us towards demanding a complete metaphysical description of reality that includes psi as a real component.
Fundamental physical variable, the fundamental description of the interaction. The wave function simply describes how the particle's probability distribution responds to that interaction. The fact that the particle doesn't need to physically enter the region merely reflects the non-local nature of information distribution within quantum physics, which we already accept. It is still an operational calculation that successfully predicts the interference pattern shift. Look, we have established that the standard quantum formalism offers internally consistent, robust frameworks, whether through the historical Copenhagen operational view or the modern, more refined relational and information-theoretic interpretations like cubism and RQM. By treating the quantum state as fundamentally informational or relational, we preserve locality, we avoid the measurement problem paradox, and we accept that quantum mechanics isn't a God's eye view of an external reality, but rather a universal guide for interactions and observer experience.
And conversely, we remain committed to the Einsteinian perspective that a physical theory must strive for a complete and objective description of reality. The conceptual crisis surrounding the measurement problem is not trivial. It's a profound failing in the standard framework that demands resolution. The existence of viable, complete alternatives, whether deterministic and explicitly non-local like Bohmian mechanics or stochastically objective and testable like CSL, proves that the debate over the ontological status of psi is far from settled. In fact, due to new experimental physics designed to test collapse models, this historical philosophical argument has now entered its most critical phase of experimental investigation.
Ultimately, this debate forces us to choose allegiance to one of the great commitments of physics: operational coherence and consistency, or the persistent, relentless pursuit of a complete, objective, observer-independent description of physical reality.
And so we leave the listeners with the ultimate question, echoing those famous arguments of Bohr and Einstein. Which commitment better serves the progress of physics today?